So for reference, this is the 5-volt rail, and the other side is the 3.3 rail. So what we have here is the thermocouple and the sphere ball. So the sphere ball is wired through here, these pins tightened down, and with the thermocouple, how to connect it is with V in. You want to connect it to the 3.3 rail. 3VO is not used in this lab. Ground is connected to the ground rail and the microcontrollers ground rail too. So, and the next part is DO. DO is the data, which is connected to the PC2 on the microcontroller. CS is chip select and is connected to PB15 as a source or push-pull when doing it on IDE. And CLK is the clock, which is connected to PB10. So here's how I conducted the experiment. I already took the data, but what I did was first put the ball in hot water and let it sit for a while till it's constant, as seen in this graph. And then what I did next, after the temperature of the ball was in steady state, I would just put it in the cold water and let it stay. And all the values were outputted to PuTTY and copied to Excel. We'll show you that my circuit works. So it is currently in lukewarm water, and if I look at the PuTTY, there's currently some data points, but if I press the blue button, it will reset and start collecting data points, and as you can see, it's in lukewarm water and the temperature is increasing over time. And if it's in cold water, then we'll see that it is slowly decreasing. As you can see in this graph, these are all graphed, and you see that hot temperature is in steady state, and then this is where it is dropped in cold water, where it cools down to a steady state cool temperature. We want to shift all the values down so it approaches T infinity to get a exponent on Excel, and we also want to make the y value here become t as a function of time minus T infinity divided by T initial minus T infinity. So here is where I shifted it, and here's where it was all scaled down. To find the convective heat transfer coefficient, so going through this process, when y equals t is a function of time minus T infinity divided by T initial minus T infinity, we're going to get this value, take the natural log, and eventually stuff will cancel out, and you can plug in the properties and constants found in the Bergman's heat transfer book, and I got a heat transfer coefficient of 601.63 watts per meter squared Kelvin. And in table 1.1 in the book, we see that it is in the free convection range for liquids, so this value makes sense.